So good morning all. Welcome to the last lecture, that is 10th lecture of Unit 4. Today we are going to discuss about the attenuation in optical fibers. So attenuation can also be called in the simple language like losses in the optical fiber. So when light travels along the fiber, there is a loss of optical power which is called as attenuation. So attenuation is nothing but ratio of output optical input power to the optical output power, Pi by P naught. So the power transmitted into the fiber from an optical source is called as Pi, and the power received at the fiber end is taken as output power P naught. So the relation defines the signal attenuation or absorption coefficient in terms of length L of the fiber. So usually indicated with the formula like alpha is equal to attenuation alpha is equal to 10 by L log 10 Pi by P naught. So for 1 meter, if you take log 10 Pi by P naught, we can take it as. So length L of the optical fiber is expressed in kilometers and the attenuation is expressed in decibels per kilometer. So decibels is the other unit you all know for noise. Here this loss is nothing but the unwanted signal. So same decibels is used for the loss in the calculation of attenuations in optical fibers. So now what are the main causes for creating this attenuation is, one is absorption, second one is scattering, and third one is bending losses. So each mechanism of loss is influenced by the properties of fiber material and fiber structure. Absorption losses over a length L of fiber can be described by the usual exponential law for light intensity or irradiations, like I is equal to I naught e power minus alpha L, where I naught is the initial intensity and we can say that alpha is attenuation for over a length L of the optical fiber. So if you see the graph for the wavelength for any particular wavelength and the attenuation, the scattering plays at the initial wavelengths and absorption are at higher wavelengths. The attenuation profile is shown in this figure, which is a graph between the wavelength and the loss. In the figure, absorption peaks of 1.25 micrometers and 1.4 are observed, which are respectively due to the peculiarities of the single mode fiber and the traces of water remaining in the fiber as an impurity. So the absorption is mainly due to the oxyhydroxyl ions present in the fiber during the manufacturing, or we are manufacturing the optical fibers by like modifying the silicon dioxide, which is sand, and by modifying the silicon dioxide into the glass, usually water vapor will be present, and that water vapor is the main cause for the absorptions of loss signals in the optical fiber. So 0.5 decibels per kilometer at 1310 nanometer and 0.25 decibels at 1550 nanometers. So when you increase at higher wavelengths, the losses will be reduced. A pulse of now the second point is dispersion of the light. A pulse of light sent into a fiber broaden in time as it propagates through the fiber. This is called as pulse dispersion. It means broadening of the signal. This we have already initiated in the intermodal dispersion. So different rays takes different times to propagate through the given wavelength of the fiber. So the travel with different speeds, and intramodal is any given source emits over a range of wavelength, and because of the intrinsic property of the material of the fiber, different wavelengths take different amounts of time to propagate along the same path. That's why intermodal dispersion will be more in the case of step index fibers because the refractive index is uniform. But in the graded index fibers, since the refractive index is variant, they travel with different intervals of time. So that's why there will be less loss in of the intermodal dispersion. So dispersion occurs when photons from the same light pulse take slight different paths along the optical fiber. Because some paths will be longer or shorter than the other paths, the photons will arrive at different times, thus mirroring the shape of the pulse. So over long distances, one pulse may merge with another pulse, and when this happens, the receiving device will not be able to distinguish between pulses. That is called as broadening of the pulse. So pulse dispersion in the optical fibers is a phenomenon in which the phase velocity of the wave depends on its frequency, and such medium is called as dispersive medium. So this dispersive medium, intermodal dispersion, can be reduced by using the graded index fibers. This part we have already discussed in the case of types of optical fibers. And there are several factors that cause dispersion in the optical fibers. In multimode fibers, different axial speeds of different traverse modes cause intermodal dispersion. On single mode fibers, chromatic dispersion is eliminated, occurs because of the slight variation in the index of the glass with the wavelength of the light. Dispersion limits the bandwidth of the fiber because the spreading of optical pulses limit the rate that pulses can follow one another on the fiber and still indistinguishable at the receiver. So chromatic dispersion is nothing but the color variation. When light passes through a prism, some of the wavelength bends more because their refractive index is higher and they travel slower spectrum of white light. The red and orange light travel slower and so are bent. So most while the violet and blue travel faster and so are bent less. All the other colors lies in between them. So this dispersion can be reduced depending on the wavelength that we used. So we have discussed about the attenuations in the optical fibers. So attenuations are mainly due to the absorption, scattering, and these chromatic aberrations. And the next topic is basic problems based on the formulas that we have calculated. So the problems are mainly calculating the numerical aperture. Here the refractive indices of core and cladding are given and we have to calculate the numerical aperture. Numerical aperture is already we have derived the formula as sine inverse root of mu1 square minus mu2 square or n1 square minus n2 square. And if you substitute these values, the answer is 34.6 degrees. And this is the maximum incidence angle and the numerical aperture is 0.568. Remember that there will be no unit for the numerical aperture, but the incidence angle is theta. Similarly, the second problem is the refractive index of core is given and the cladding is given. We have to calculate the fractional refractive index and the numerical aperture. Fractional refractive index is n1 minus n2 by n1. If we substitute, we get 1.33. Numerical aperture is root of n1 square minus n2 square. We get this answer. And the acceptance angle is sine inverse root of n1 square minus n2 square. So we get 14.13 degrees. And the third numerics is calculate the refractive indices of core and cladding given that fractional change in the refractive index is given and the numerical aperture is given. So it's somewhat like reverse in the problem. So del mu r is equal to mu core minus mu n core n1 minus n2 by n1. So if I substitute that value, we get n1 is equal to 1.424, n2 is equal to 0.988 and so on. So these are the simple problems based on the formulas that we have derived from the numerical aperture and the acceptance angle and fractional change in the refractive index. So with this we have finished all 10 units of fourth unit. In this particular class, we have discussed about the attenuations in the optical fibers and 4 numeric problems based on the numerical apertures and acceptance angle. Thank you.